In this video, we are going to examine intramolecular bonding. Intramolecular literally means inside of a molecule. Molecules, though, are made up of atoms. And so when we talk about inside a molecule, we're talking about the connections between the atoms that actually form the molecule. This has been previously examined to some extent, but in this video, we want to go a little bit further with distinguishing the nature of the connections between atoms that make up a molecule. So let's consider different aspects of bonding in general. First, we're talking about valence electrons. We're talking about the electrons on the very outside of an atom. Those are the electrons that when two atoms approach one another are going to be the first ones to be encountered and would be available for helping two atoms join with one another. Realize, as we've discussed previously, the goal is to have a system that is more stable, that reaches a lower energy state, and achieves, in this situation, an octet of valence electrons or a duet, depending on exactly where we are on the periodic table. Now, we classify elements based upon what they're doing with those valence electrons. And the two general categories that we've discussed previously are metals and nonmetals. Metals are found to the left-hand side of the periodic table, and we know that in order to get to an octet, they are going to tend to donate one or more electrons and undergo what we call oxidation. Nonmetals found on the right-hand side of the periodic table, on the other hand, are trying to pick up one or more electrons to get to an octet and therefore undergo what we call reduction. Let's see how those kinds of elements will interact when they go to form a bond. So, two considerations. The first, let's consider when a metal and a nonmetal approach one another. They're aiming to get an octet. They're aiming to achieve electronic stability. These seem perfectly aligned with one another. Metals tend to want to donate electrons, be oxidized. Nonmetals want to accept and be reduced. So it seems they're perfectly matched to exchange electrons. The metal will pass the electrons that it's trying to get rid of and hand them over to a nonmetal. As soon as that happens, of course, the atoms are no longer going to be neutral. The metal, having lost one or more electrons, will now become positively charged and form an ion called a cation. And the nonmetal, having accepted one or more electrons, will no longer be neutral, will have an excess of electrons compared to protons, and will form a negative ion called an anion. The cation and the anion then, though they've achieved electronic stability, they will be attracted to each other, and there will be an electrostatic attraction that holds the two ions together and essentially is the nature of an ionic bond. These are very strong bonds. Evidence here with this data on table salt, sodium chloride, having a melting point of 801 degrees, over 800 degrees, and a bond energy that is approaching 800 kilojoules per mole. Very difficult to pull that cation and anion apart. Now, we know there aren't really molecules of ionic compounds. We know they form a 3D grid. Here is a photomicrograph of some salt crystals. When we magnify them, we can see they have very regular cubic-shaped configurations. We know that really reflects the crystal lattice 3D grid array that the sodium and chloride ions form. So what goes on a macroscopic level reflects what's happening on a atomic level. Let's look at another consideration, and that is the eventuality of two nonmetals coming together to form a bond. When two nonmetals bond, of course, they both need some electrons, and so they are going to want to be reduced. And the only way for both of the nonmetal atoms to be satisfied would have to be achieved through the sharing of electrons. And therefore, the electrons end up belonging to both atoms. And so it is the orbiting of the electrons back and forth between the two atoms that actually ties them together and is the origin of a covalent bond. Covalent bonds are substantially weaker than ionic bonds. For example, a carbon-carbon single bond has a bond energy of only 347 kilojoules per mole, so less than half that we depicted for a sodium chloride bond, ionic bond. Now, we've talked about this before. We've talked about ionic and covalent bonds, but as with many things in chemistry, there is more to the story. And our addition to this particular story has to do with something called electronegativity. And electronegativity is a scale or a measurement of the tendency of an atom to attract the electrons that it potentially will share with another atom. The higher the electronegativity value associated with a particular element, the greater the attraction for electrons. So Linus Pauling, who was a very renowned chemist, came up with a scale that ranges from 0 to 4, 0 being low electronegativity, 4 being high electronegativity. And this rating system gives us a relative indicator of how much a particular element needs to pick up extra electrons. Here's the actual electronegativity table. You can see that the highest values are towards the right and upwards. So the upper right-hand corner, particularly nitrogen, oxygen, fluorine, and chlorine, have high electronegativities. That makes perfect sense. Nonmetals need to pick up electrons. They would tend to want to attract electrons more extensively. On the left-hand side, and going down lower, you have greater metallic properties. Metals like to be oxidized, so they would have a lesser attraction for electrons. They're trying to get rid of, they're trying to oxidize. Below the main table, though, is a decision table that lets us look at the difference between the electronegativities of two atoms that are bonding to each other and have a judgment about the likely bond that would exist between those atoms. This is merely a guide. The fundamental facts about bonding have not changed. If a metal bonds to a nonmetal, there's going to be an exchange of electrons, an ionic bond will form. If two nonmetals encounter each other and bond to each other, they're going to want to share electrons, and you will get a covalent bond. It's really distinguishing between what kind of covalent bond do we end up with. So, what are the possibilities? Well, at one end of the extreme, of course, is when you have a metal and a nonmetal encountering each other and exchanging electrons, and forms an ionic bond, here depicted again by sodium chloride. Sodium had 11 electrons. It donated its outermost electron in the third shell. It did not just simply disappear into thin air. It was transferred over to a chlorine atom, and the chlorine atom picks up an extra electron, now has 18. In both situations now, there is an unevenness between protons and electrons. So the sodium atom became a sodium ion, a cation, and the chlorine atom became a chloride ion, a negative ion. And of course, they're held together because opposites attract. That's one end of the spectrum. At the other end of the spectrum, we have what are called pure covalent bonds. And pure covalent bonds are going to form when there are two nonmetals that are sharing electrons. They have similar electronegativities, and they share those electrons equally. Here, this is depicted by this hydrogen molecule formed from two hydrogen atoms. Both are nonmetals. Both would like to pick up one more electron and have a full first shell with two electrons. And so they both pull one of their electrons, that one electron, and you can see the pair of electrons now are part of the orbits of both of these hydrogen atoms, forming a hydrogen molecule. Those electrons are evenly distributed. They are not concentrated in over one atom or another, and therefore this is a pure covalent bond. But now we have a third possibility, sort of in between those extremes, where we have two nonmetals joined together, but they do not share the electrons equally because their electronegativities become more and more dissimilar. In this situation, the shared electrons will drift towards the more electronegative element. Here you see this depicted in a hydrogen fluoride molecule. Two nonmetals, hydrogen and fluorine, but fluorine having a really high electronegativity, 4.0, and hydrogen only having a value of 2.1. So the electrons are not totally stripped off of the hydrogen, but they spend much more time towards the fluorine end of the molecule. That's depicted in the electron density diagram itself, and it's secondarily depicted by the arrow that I've drawn. The arrow points from the less electronegative to the higher electronegative element, showing where the electrons are drifting. And then I've drawn a tail on the arrow, and that tail forms a plus sign. So the hydrogen end of the molecule becomes a little bit positive because it's a bit deficient in electrons. This is a polar covalent bond. We had not run into those previously. We're able to predict their existence through the use of electronegativity. Now, once you know what's going on with the bonds between the atoms that form the molecule, you can start to characterize molecules. What is their overall character, looking at the entire molecule? And one possibility are nonpolar molecules. So this would be a situation where there is an even distribution of electrons across the whole molecule. That is depicted here in this chlorine molecule, where the two chlorine atoms are sharing a pair of electrons. They have the same electronegativity, 3.0. They spend no more time around one chlorine atom as opposed to the other. There's an absolutely equal distribution. I do not see any poles. I don't see a positive area and a negative area. There is no separation of charge, and that's why I characterize this as a nonpolar molecule. On the other hand, I could have two nonmetals sharing electrons, but because of a significant difference in their electronegativities, I end up with an uneven distribution of electrons. The more extreme example of this is in an ionic bond, an ionic molecule, where there's a full exchange of electrons here between the sodium and the chlorine, a single electron moving from one area to another. I definitely have polarity. I've got a positive and a negative end. So automatically, any ionic compound would have a character described as polar. Another way we can get polarity, though, is if the bonds, the intramolecular bonds, are covalent, but they're polar covalent, and the geometry starts to enter in. Okay, here you see a water molecule where the oxygen and the two hydrogens are not sharing electrons equally. they are becoming concentrated around the oxygen end of the molecule. Instead of using an arrow, I'm depicting that polarity by using the Greek letter delta, meaning partial. So there's a partial negative charge on the oxygen. The electrons have drifted away from the hydrogens, and so there's a slight deficiency, and so there's a partial positive charge on each hydrogen atom. Because of the shape of this molecule, there ends up being a positive and a negative end of the molecule. If I were characterizing this, again, I would describe it as being a polar molecule. Now, I referenced there that geometry could play a role in addition to the nature of the actual intramolecular bond. And so we have something called dipole moments. And essentially, dipole moments are going to be a vector depiction of what the distribution of electrons are in a molecule. Rather than reading through these definitions you see here, let's look at specific examples using diagrams and vectors and see if we can figure out whether a dipole moment exists or not. So let's first of all look at the situation where I do have polar bonds, but there ends up being no dipole moment, no uneven distribution of electrons. This carbon dioxide molecule has exactly this geometry you see here. It is linear. The angle between those two double bonds is 180 degrees. The individual double bonds, carbon-oxygen double bonds, are polar covalent. And I'm depicting them here using the arrows, using vectors. They point from the less electronegative element to the more electronegative element, so from the carbon to the oxygen. Again, the tail on both those arrows tells you that the carbon is going to be a little bit positive. If those were truly vectors, and let's say they represented forces, this would be two people pulling in exactly opposite directions on an object with equal force. Of course, the object would move nowhere. So, in our situation, that means there is no dipole moment. And if there is no dipole moment, the character of this molecule is nonpolar. So you can see how geometry could enter into our consideration about the character of a molecule. The same thing happens here with this boron trichloride molecule. 3 polar covalent bonds arranged in this trigonal planar, it's totally flat configuration. And there's 120 degrees between each of those bonds. If we drew in our arrows, they would point from the boron towards the chlorines because they have a higher electronegativity. This would be like 3 people of equal strength pulling on an object at evenly spaced positions. And of course, the object would not move anywhere. They would cancel out. So again, we would have no dipole moment, and this molecule also is nonpolar. So when you want to evaluate, is there a dipole moment, and therefore what would their character be for the molecule, you have to consider 2 things. What is the intramolecular bond, and what is the geometry? Now, it's possible that the geometry causes the vectors not to cancel out, and we end up with a dipole moment. Let's go back to that water molecule, and let's put the arrows in. Here, the oxygen-hydrogen bonds are polar covalent. The arrows depicting that status go from the hydrogen with lower electronegativity towards the oxygen, but they're at an angle to each other. They're not opposing each other. They're actually going to add to one another. The bigger arrow shows you the resultant vector that you would get, and that would be the direction of the dipole moment. Clearly, it is not equal to 0. Therefore, one end of the molecule is slightly negative, and one end of the molecule is slightly positive. And so, therefore, we would describe the character of a water molecule as being polar. In this like manner, this nitrogen trifluoride molecule, the geometry, again, is having an impact where the vectors don't cancel. This is trying to depict a nitrogen atom sitting at the apex of a trigonal pyramid, like a pyramid. The fluorines are at the feet, form the footing for the pyramid. Again, the vectors point from the less electronegative towards the higher electronegative element, so they're pointing downward. So if these were three forces, so three people pulling with equal force downward on an object, clearly, again, they're not going to cancel each other out. That object would move straight downward, and that is conveyed through the arrow on the far right of our diagram. That is the direction of the dipole moment. So a dipole moment exists, and again, the character of this molecule would be polar. So you have to consider the intramolecular bond, and you have to consider the geometry to decide, yes, you have a dipole moment, therefore it is a polar molecule, or no, there is no dipole moment, and it is a nonpolar molecule. Put these polar molecules in an electrical field, much like what you did previously in the little FET molecular polarity activity, and they're going to respond to that electrical field because, of course, inside the electrical field you would have plates that have positive and negative charges, and therefore would attract the positive or negative ends of molecules, and they will align themselves with the electrical field, and they would actually migrate. They would rotate and migrate in an appropriate direction. You saw that in your activity. That was very revealing. It helps to drive home the idea of what character means for a molecule.